everyone. Hello, everyone. My name is Lu Jie. My presentation title is CrashTuner, detecting crash recovery bugs in cloud system via meta-info analysis. Recovery must be the first class operation of distributed systems because the nodes in the distributed systems can crash due to different reasons, like hardware failure, power down, and software bugs. Node crash events can also be very common in a largest cluster. For example, in at least 180 nodes will crash each day in Google cluster, who has about 12,000 of nodes. But the crash recovery code can be buggy and often result in CATOS traffic failure. Many exciting detection approaches are developed to hunt such bugs, but these approaches still have some limitation. For example, random photo injection is ineffective, and mode checking is inefficient and requires manual specification. So crash recovery bugs still widely exist in distributed system. These bugs are hard to detect because distributed systems have large state space to explore. And most of them can only be triggered when nodes crash under special time condition. In this paper, we present the CrashTuner, a new approach to automatically detect crash recovery bugs in distributed systems. We have CrashTuner can finish test 5 distributed systems in 35 hours and report 21 new crash recovery bugs, including 10 critical bugs. So how does CrashTuner do it? First, we performed a crash recovery bug study. We found that exciting crash recovery bugs can be easily triggered when nodes crash before reading variables or crash after writing variables. We also find we find that all these variables have one thing in common. They are all the meta-info variables. So we will use a simplified young example to explain what are meta-info variables. When user submit a job, Young will have an application to track it. The application will start an attempt to perform the job. The attempt will run in one container, which is the abstraction of a resource in one node. The attempt will split the large job into small tasks. Each task also has its own attempt. Each attempt also runs in one container. So the terms like nodes, jobs, tasks, containers are the abstract state of a distributed system. We call such abstraction as meta-info. Instances of these abstractions are meta-info values. These values make up of high-level system status. These meta-info values are stored in meta-info variables. So let's see a bug example. When node crash, which will triggered when node crash before reading meta-info variables. This is a new bug come from Yang. Task 1 is running on node 2. Yang will have a variable to track it. But node 2 crash. Recovery detect the crash and update the meta-info value as update the meta-info variable as the new value. Young will Young will read the meta-info variable without being aware of the change. So it still thinks the meta-info value is the old one. So it will allocate resource. So it will allocate resource to the uninitialized task. Hence a bug happens. So how CrashTuner detect it? So before reading the meta-info variable, CrashTuner inject sleep. Then and crash and then crash the node 2 to update the meta info variable. Then let young go and read the uninitialized value. So this bug should happens. This is let's say another bug example, which will trigger the one node crash after writing meta info variables. When the slaves join the cluster tracker will write it into online service, which is a meta info variable. The slave node also regests to RuneKeeper. When when the node crash, RuneKeeper detect the crash and tell the recovery process to remove the dead node from online service. But if the crash if the node crashes after the crash just after the crash tracker writing the meta info variable, the dead node will still exit in online service. So when Hmaster read the meta info variable, it still think the dead node is alive. So it will connect the dead node again and again, and print thousands of nodes. The master hangs. So how CrashTuner detected? After class tracker has written the slave node into online service, CrashTuner crash the node 2 and make the dead node still exit in online service. Then the master will read the meta info variable and find the dead node is still alive, and this bug should happens. So how to find the meta info variables? First, the node reference variables are meta info variables. We will use log analysis to find the node reference variables. For example, in this log pointer, it has a variable node ID. We will parse the log statement into regular expression, then match the log instance. We can find that node ID has the value headable 14, which is the host name of one node. So node ID is the meta info variable. Second, meta info variables related to meta info variables are also meta info variables. Two variables are related when they appear in same log instance. Take this log point for example. Node ID is meta info variable. So content ID is also the meta info variable because they appears in the same log instance. So in this log point shows that a temp is also the meta info variable. We also use a type-based static analysis to discover meta info variable which are not logged. So the crash pointer are period pointers of meta info variables or post-write pointers of meta info variables. When we find all crash pointers, we will send them to our filter injection framework for testing. But we still have a problem to resolve. Which node to crash? When node 1 is reading or writing the meta info value related to node 2. So the crash. So we need to crash node 2 at the crash pointer in node 1. As we mentioned earlier, one log instance will print two meta info value in together. For example, this for log instance shows that container 1 and temp 1 is on headable 14, container 2 and temp 2 is on headable 15. So we can use online log analysis to actuate the meta info values. If two meta info values and send them to meta-info manager. If two meta-info values appears in the same log instance, we will record them together. When the trigger part when we want to when CrashTuner will use a meta-info values to query the meta-info manager. The manager will check whether the whether the meta-info values appears together with a host name. If yes, it will send the host name back to the CrashTuner. CrashTuner then will crash the corresponding node. We have applied CrashTuner on 5 distributed systems, and Consumption is not our bug study system. We find that CrashTuner only found 1,056 correspondence. That means CrashTuner reduced more than 99% unnecessary correspondence. CrashTuner reports 21 new bugs, 60 of them are already fixed. We also compare CrashTuner with random fault injection and IO round crash injection. We find that CrashTuner is much more efficient and effective than these two approaches. CrashTuner may not be good. CrashTuner also have some limitations. For example, CrashTuner may be not good enough to test the system with bad log quality. Developer can annotate the meta-info type to resolve this limitation. CrashTuner only injects one crash event. We can extend CrashTuner to test the 2 or more crash events in the future. And CrashTuner only tests the Java-based system, but our study on Kubernetes shows that it also has meta-info-related crash recovery bugs. We are extending CrashTuner to work with the system written by Golang and C++. Many excellent work have inspired our research. Thanks to them. Finally, I want to use these words from operating systems 3 easy pieces to show the key point of CrashTuner. Abstraction is so fundamental that sometimes we forgot its importance, but we want to hear. We find that meta-info is a well-suited abstraction for distributed system. We believe that this also can help other technologies such as model checking. Thank you. Any questions?
All right, we have plenty of time for questions. Yes.
Hi, Sixiang from the Ohio State University. I do not quite understand the error, the bug in your second example when a heartbeat is sent and the node is crashed, and the client cannot get the data that he or she wants. Why this is a bug? I think that is a correct response from the server.
Sorry.
Is it?
The client, what?
Oh, so can you go back to the your second example?
This is the second
run?
example. And
Sorry, I can't. Okay.
this is the first or the second?
The second one.
The second one. This one.
Yeah.
Mm-hmm.
So why do you call it why this is a bug? So my question is.
Because the recovery process disappear. If we inject the crash here, that is okay because the recovery process will remove the dead node from online service. But if we crash node to add here, the recovery process will disappear. Then the dead node will left in online service. It must read the online service and find that this has a check. It finds that the dead node still exit in the online service, so it will try and try, but actually, node 2 is dead.
Yeah. So my point is that Zookeeper take times to detect the failure. So personally, I think the reader have, for example, if you return a non-pointer or something, that's what is expected because the node is failed. Yeah,
Oh.
we can talk more offline. I think.
Okay.
We have another.
Hi, I'm Vastav from University of British Columbia. My question is, for finding meta-info variables, what is your false positive rate? Because logs and log statements might not actually have only the meta-info variables. They may also have some extraneous information that is not really describing the meta-info state of systems.
Sorry, pardon. Could you speak louder?
Okay. So my question is, what is your false positive rate for finding meta-info variables? Because log statements might not actually just have meta-info variables as part of it. They may have some other variables that do not describe the meta-info state of distributed systems.
Sorry, I don't really understand your questions. So can we talk offline?
Sure.
Yeah.
So I guess I wanted to follow up on that. So maybe a different way to ask is there any human filtering for meta-info variables that you found that are not necessarily useful? Do you have to go through them manually and then exclude some of them?
No manual.
No manual effort?
Yeah.
Okay. All right. If there are no further questions, let's thank the speaker again.
Thank you.